So this lecture is on the urinary system. And quick review of the structures of the urinary system. We have two kidneys, so they are paired. The one on the right sits a little bit lower than the one on the left because it is crowded by the large liver. They each have a tube that is leading the urine that was produced in the kidney from the kidney to the urinary bladder will be stored. And one urinary bladder with a urethra that will lead the urine to the external environment. Functions of the kidney include control of the volume and the makeup of the blood. It will control how much water is kept into the bloodstream, and also the excretion of various salts, or in aqueous solution, the ions that are carried in the plasma of the blood, and also the number of red blood cells. And in our endocrine chapter, we learned that the kidney does secrete a hormone called erythropoietin, and that acted on the bone marrow to trigger hematopoietic stem cells to divide and make more red blood cells. We'll also see that the kidneys perform acid-base balance of the blood, and lecture next week is going to focus on the mechanisms in which it does that. And it's responsible for excretion of metabolic and foreign waste and the activation of vitamin D. So vitamin D ultimately is produced as a precursor in the skin. When UV light strikes vitamin D enters the bloodstream, goes through the liver, and the liver activates vitamin D, and then its final activation by enzymatic activity occurs in the kidney, and then it's ready for physiological use. Table 14.1 is going to list the various functions of the kidney, most of which we'll be covering in this lecture today, so it's a nice review table that lists the functions. And internally, the kidney is arranged into different layers of tissue. The outer layer is called the cortex. The cortex is where the nephrons are actually going to be located, and it is the nephron that actually produces the urine. Then the urine is led through the medulla. If you recall, the medulla is organized into pyramids called medullary pyramids, and contains blood supply and collecting ducts from the nephron. The collecting duct will dribble the urine into the pelvis, and so the pelvis will kind of funnel the urine that's coming from the medullary pyramids into the ureter, where it will make its journey to the bladder to be stored. Now, the nephrons were the structural and functional unit of the kidney, and they are ultimately responsible for the control of mineral balance, so various ions will be reabsorbed or excreted along the nephron tubules, as well as water balance control, which can be reabsorbed throughout the length of the nephron tubules. And there are two types of nephrons, and one is called cortical and the other is called juxtamedullary. The cortical nephrons and juxtamedullary nephrons are named so because of their position in the kidney. So when we look at the kidney, and instead of drawing pyramids, I'm just going to try to simplify this. The cortex is on the outer layer, and the medulla was more towards the center or core of the kidney. Now, cortical nephrons refer to being completely contained within the cortex. So you'd have your glomerulus within the Bowman's capsule, and then your proximal convoluted tubule, loop of Henle, distal convoluted tubule, and then the collecting duct runs through the medulla. So the entire nephron is contained within the cortex. Now, juxtamedullary, juxta means next to or neighboring. Get their name because the nephron is so close to the medulla, the loop of Henle will actually dip into the medulla, so they are more next to the medulla and look something more like this. And then the collecting duct travels through the medulla. Sorry. All right, so with the cortical nephrons, the blood supply after the glomerulus becomes the efferent arteriole, leaving the glomerulus, and then is going to become the second capillary bed. This is a portal system. called the peritubular capillaries. So you're going to have your glomerulus, and that was fed by an afferent arteriole, and then blood will leave in the efferent arteriole, and then the peritubular capillaries surround the nephron tubules like so. So peri around tubular, the tubules of the nephron. Whereas the juxtamedullary nephron is going to have vasa recta. Now vasa in Latin means vessel, the way we would use it in English, like a vessel of the cardiovascular system. Recta means straight. So these are the straight vessels. So you still have a glomerulus and an afferent and an efferent arteriole, and the blood supply will wrap around the tubules, but then they become long, straight capillaries around the nephron, and they've got some horizontally running capillaries in there as well, but they're much straighter rather than tightly coiled around the tubules of the nephron. And so these are the vasa recta, and the cortical nephrons just have peritubular capillaries. Figure 14.3 in your textbook shows you the difference between the cortical nephrons and the juxtamedullary nephrons. The cortical nephrons are almost entirely contained within the cortex region of the kidney. The loop of Henle may dip a little bit into the medulla, but the juxtamedullary nephrons are much closer to the medulla, and their loop of Henle does extend deep into the medullary tissue. And that is going to provide a greater efficiency in water reabsorption, which we'll see a little bit later with the loop of Henle, in the juxtamedullary nephrons. Now, humans have about 80 to 85% juxtamedullary nephrons, which means we are really efficient at reabsorbing water from the urine that is being produced in the tubules of the nephron. All right, now the general processes of the production of urine is going to include filtration. So a Bowman's capsule, we're going to filter. And so glomerular filtration is shown here at the capsule. And we're going to have filtrate, which is going to be the fluid from the bloodstream that is filtered out of the bloodstream and captured by Bowman's capsule and will enter the tubular system. From there, two additional processes will occur. One process to secrete, which is an active process, uses ATP, substances that need to leave the body in excretion with the urine, but were too large to be filtered through the glomerulus and taken up by Bowman's capsule. So we can use ATP and pumps to move substances that need to be excreted via secretion from the peritubular capillaries and into the tubule system of the nephron. We can also do reabsorption along the nephron tubules, and reabsorption will be of substances such as water and ions that are necessary to keep into the bloodstream that we don't necessarily want peeing out. That will also include glucose. Anything that is small enough to make it out of the filter, the glomerulus, of the nephron will get filtered, and that will include very small glucose molecules. In the healthy condition, the kidney is so good at reabsorption that all of the glucose molecules that make it through the filter get reabsorbed into the peritubular capillaries. However, in diabetic conditions, as we've mentioned with lab before, if we exceed the threshold in which the kidney can reabsorb, then that glucose does end up being excreted with the urine. And the final process of the urinary system is urinary excretion, which we'll talk about later as micturition, or more commonly called voiding or urinating. Okay, urinary excretion. All right. So filtration in the glomerulus is going to lead off this process. So the glomerular capillaries are fenestrated. They are very similar to the capillaries that are in the intestines. They not only have intercellular clefts, holding the cells together of the capillary, but they also have pores in the cells themselves. So a large amount of molecules can pass through. They will still be small molecules, things like gases. So we do find that gases do get dissolved into the urine. Also, waste molecules such as urea, okay, water, amino acids, vitamins, etc. And so we do quite a large amount of that because not only do the capillaries have the intracellular clefts, but they also have the fenestrations or pores. So a large amount of these small substances can pass from the blood supply and be captured by Bowman's capsule and led into the tubular system as filtrate. Now there are two main forces that act to push filtrate out of the bloodstream, and these are factors that you've seen before in regular capillary exchange when we talked about the importance of the lymphatic system, and that is hydrostatic pressure and osmotic pressure. Hydrostatic pressure is going to force substances out, whereas osmotic pressure is going to be set up by a solute gradient, and therefore water will follow by osmosis. Now here, the solute gradient is set up the same way that we saw before in regular capillaries. It's by a protein called albumin that is produced by the liver and put into the bloodstream. But albumin is going to be in a little bit higher concentration as it passes through the kidney. And so we're going to see a little bit different pressure than we saw in regular capillaries in just a few minutes. So again, water, waste molecules, nutrients, vitamins, amino acids are all going to be filtered out of the glomerulus. Now, that doesn't mean that just because they're small enough to be filtered, we want them to filter. All of these things were things that were absorbed by the digestive system on purpose that we want for the body. And so the kidney does have processes to reabsorb those things that made it through the filter and be put back into the bloodstream via the peritubular capillaries. All right, so this is Bowman's capsule, figure 14.5. So just as a quick review as to what's happening in this nephron from anatomy, you're going to have your afferent arteriole, and so blood is traveling towards the filter in this blood vessel. And then this is your glomerulus, your small ball of fenestrated capillaries. So as the blood moves through the glomerulus, you're going to have water and solutes that are small enough to get through the filter leave the glomerulus into capsular space. So this is just the space between Bowman's capsule and the glomerulus itself. And then Bowman's capsule will route everything that's getting filtered, which we now call filtrate, into the tubule system of the nephron. And then the blood will leave the filter in the efferent arteriole, which of course will become the peritubular capillaries, which are important for filtration and tubular secretion. Sorry, not filtration, my apologies. Which is important for tubular absorption and secretion. All right, so everything that crosses out of the capillary and into the tubular system is going to have to cross the filtration membrane. And the filtration membrane is formed by the endothelial cells of the capillary, some basement membrane, which of course is always associated with epithelia, and then we have our podocytes. So if you remember podocytes from your anatomy class, they are modified smooth muscle cells that have pseudopods or extensions that interdigitate with the other pseudopods of the other podocytes, and they completely surround these fenestrated capillaries. And so whatever leaves the capillary through the intracellular clefts of the capillary and diffuses through the basement membrane will have to pass between the pseudopods of the podocytes. And so typically things that are small enough to get across this entire filtration membrane are small molecules, water, ions or electrolytes, glucose, amino acids, fatty acids, which are lipid soluble, vitamins, urea, also lipid soluble, uric acid, creatinine. These last three are all waste that has to be excreted from the body. All right, so net filtration pressure is therefore set up by a couple of different pressures. Hydrostatic pressure, which of course is the pressure of the blood against the wall of the capillary that forces substances out. That's going to be counteracted by osmotic pressure, which of course is set up by the protein gradient of albumin. It's a little bit higher as it passes through the capillaries of the kidney at 29 millimeters of mercury. That's going to draw substances back in by osmosis. But now we have a third pressure that we did not have in regular capillary exchange. This pressure is caused by the fact that the glomerulus is surrounded by a Bowman's capsule. So you're going to have your afferent arteriole leading blood into the glomerulus. And then you have your little ball of capillaries where filtration occurs. And then blood's going to leave the glomerulus and become the efferent arteriole, traveling that direction. So surrounding this ball of capillaries, which we don't have in other capillaries of the body, is literally a capsule end of a tube. And this capsule end of a tube provides some back pressure. And so as filtrate comes out of that glomerulus, like this, it fills up this space and builds up pressure within the space, and that's known as capsular pressure. And so we're going to have three different pressures that are being exerted in this system. Hydrostatic pressure is the pressure forcing out, and that's at 60 millimeters of mercury in the glomeruli of the capillary. We're also going to have colloidal osmotic pressure, which is drawing substances back in at 29 millimeters of mercury. Hg. And then we have capsular pressure, which is also pushing back at 15 millimeters of mercury. So we have slightly different math to do here than we did in regular capillaries. You have 60 millimeters of mercury out. So since the other two are in, we're going to subtract them. So we're going to subtract 29 and 15, which was capsular pressure, and osmotic pressure from 60, which leaves us with 16 millimeters of mercury. That's a positive number, so that means out, and therefore filtration. And will leave the bloodstream and enter the tubular system of the nephron. Okay, so the overall pressure is going to be 16 millimeters of mercury out, collected by Bowman's capsule and routed into the tubular system. Now, glomerular filtration happens at a rate as well, so the pressure contributes to the rate. And so the rate is how fast that filtrate leaves the bloodstream over a period of time. And the normal, healthy, average rate for glomerular filtration is 125 milliliters a minute in the kidney. Now let's convert that to a daily pressure. You won't be asked to calculate this daily pressure on your exam, but I want to show you how active these kidneys are in filtration. So to convert that, we're going to take 125 milliliters for every 1 minute, and there is 1,000 mils in 1 liter, and there are 60 minutes for every hour, and there are 24 hours in a day. Okay, so we're going to cancel out our units. And minutes cancels with minutes, milliliters cancels with milliliters, hours cancels with hours, and we're left with liters per day. And if you run that through on your calculator, it comes out to 180 liters of filtrate leaving the blood a day. Okay, in a 24-hour period. So the kidneys actually filter 180 liters. That's about 92-liter bottles of soda worth of blood running through the glomerulus in 1 day's period of time. Now, 99% of that is going to end up being reabsorbed. So we'll deal with that a little bit later, but that is your daily rate, about 180 liters of filtrate a day. All right, now you can also see how high blood pressure conditions, such as individuals that have heart failure and so forth, also have kidney trouble. If we increase our hydrostatic pressure, let's say to 70 millimeters of mercury, and osmotic pressure stays the same, and so does capsular pressure, that leaves us with 26 millimeters of mercury a day. Millimeters of mercury pushing filtrate out of the bloodstream. And that's going to be translated into a much higher glomerular filtration rate, which can lead to things like edema of the tissues of the kidney and glomerular nephritis and other types of kidney conditions. So we need to be able to control this hydrostatic pressure. All right, so figure 14.8 shows you the factors that we just discussed. So hydrostatic pressure is pushing fluids out of the bloodstream. And then we also have osmotic pressure, pi, pulling substances back in, as well as capsular space pressure, pulling pressures back in, substances back in. So if this is 60, and this is 29, and this is 15, we end up with 16 millimeters of mercury as our net glomerular filtration pressure. And that is going to have an effect on the rate at which blood is filtered in the kidney. So, as we mentioned, we need to be able to control that hydrostatic pressure. And there's two main reasons we have to control that hydrostatic pressure. One is for effective filtration. We have to have a high enough pressure to get substances out of the blood, but we also can't have too high of a pressure because it will rupture the capillaries of the glomerulus. So there are various ways that we can change the pressure in the glomerulus, which can therefore control glomerular filtration rate. So here are some of the ways that we can do that. We can control what happens at the afferent arteriole leading into the glomerulus. For example, we can constrict the afferent arteriole, which means less blood is entering the glomerulus. And so if less blood is entering, there will be less pressure in the glomerulus, which will decrease glomerular filtration rate. So that's an activity that we would want to happen if we're having high blood pressure. High blood pressure could cause this capillary to rupture, which is bad. And so we want to reduce the amount of blood leading into that filter, therefore dropping the pressure back to normal and reducing a high glomerular filtration rate back to normal. Also at the afferent arteriole, we can dilate. So down here on the bottom right. So let's say blood pressure is not high enough, and that is going to affect our glomerular filtration rate. Well, if we dilate that afferent arteriole, that means we're increasing the amount of blood by blood flow into the glomerulus. That increases our pressure back to normal, which increases that glomerular filtration rate back to normal. It's kind of like opening the floodgates of a dam. You're going to get more pressure because of more flow through the dam. Okay. Now, we can also have an effect at the efferent arteriole. So we can control what happens in that capillary by controlling how fast fluids can leave the glomerulus. So for example, if we have a low glomerular filtration rate, what we can do is limit how fast substances can leave the glomerulus by closing up or constricting the efferent arteriole. Okay, so we get a backup of substances in the glomerulus, which increases its rate. More water in the water balloon, more pressure on the walls of the vessel. And if we increase the pressure, we increase the glomerular filtration rate back to normal. We can also dilate that efferent arteriole. So if pressure is too high, we can dilate, opening the floodgates, and we get more out at a time. Okay, we're going to drain that sink faster, and therefore that's going to drop the pressure in the glomerulus behind it, dropping our glomerular filtration rate back to normal. Okay, so just for clarification, what you're seeing in this figure is the effect. The effect of these two activities will decrease the glomerular filtration rate from a high state back to normal. These two are going to increase the glomerular filtration rate from a low state back up to homeostatic values. Okay. Now, some of the processes and substances that can actually cause the afferent or efferent arterioles to vasoconstrict or vasodilate. Afferent arteriole first. So at the afferent arteriole, we can cause vasodilation, which would open the floodgates, more blood into the glomerulus, increasing the pressure, which increases the rate back to normal. This is something you've seen before. We talked about the myogenic response. That's going to be a natural response by the afferent arteriole. If we have too low of pressure traveling through the afferent arteriole, that myogenic response will cause vasodilation, opening the floodgates and allowing more blood into the glomerulus. We can also do vasoconstriction so that we can limit the amount of blood flow into the glomerulus under high blood pressure situations. Myogenic response can do that. Too high of pressure in the afferent arteriole will cause that vessel to naturally constrict down. Sympathetic nervous system, so epinephrine from the adrenal gland, norepinephrine from sympathetic neurons, as well as from the adrenal gland, can cause vasoconstriction. And can also lead to release of renin from the macula densa, which was part of the glomerular apparatus. And also ATP can actually be released from the cells of the macula densa. This is going to act as a paracrine and immediately act on the surrounding smooth muscle and cause contraction for vasoconstriction. And again, that's going to limit the amount of blood into the glomerulus, dropping the pressure back to normal. Okay. At the efferent arteriole, we can also vasodilate and vasoconstrict, as we saw in the previous figure. One example of a molecule that can cause vasodilation is prostaglandin. Prostaglandin also acts as a paracrine. It can counteract what's happening with a sympathetic nervous system. So let's say you're having a sympathetic response. We need to be able to protect those glomeruli. So this can vasodilate the efferent arteriole, opening the floodgates after the glomerulus and reducing the pressure back to normal. And vasoconstriction will occur under the angiotensin II. So if you recall from the past, renin gets released by the kidney, as we saw up here. That gets converted into that will convert angiotensinogen, which is in the bloodstream from the liver, into angiotensin I. That gets converted by an enzyme in the lungs called angiotensin converting enzyme, or ACE, into angiotensin II. And angiotensin II is a powerful vasoconstrictor. That's going to limit the amount of blood out of the glomerulus, which raises the pressure in the glomerulus, keeping adequate exchange at the glomerulus for filtration. All right, tubular reabsorption. Tubular reabsorption is where along the tubular system of the nephron, so proximal convoluted tubule, loop of Henle, and the distal convoluted tubule, we can take substances that got filtered and reclaim it back into the bloodstream. So again, things like glucose or other nutrient molecules like amino acids from the breakdown of proteins and absorption that we did in the small intestine, as well as ions that are important for homeostasis in the bloodstream. All of those are small enough to be filtered, but we don't necessarily want to pee them out, so we have a way to reclaim them, and that is with tubular reabsorption. This happens mostly in the proximal convoluted tubule, so right after the glomerulus, but we can also do some in the distal convoluted tubule and collecting duct. All of the nutrient molecules get reabsorbed at the proximal, but we can also do some sodium reabsorption, water reabsorption, and water reabsorption at the distal convoluted tubule and the collecting duct. So in figure 14.10, we can see a schematic diagram of these two opposing processes. Reabsorption is going to bring things like nutrient molecules, water, and other substances that were small enough to get through filtration, but we want to reclaim back into the peritubular system, and now they are in circulation. Secretion is going to be for substances such as excessive ions or molecules that are too big to have been filtered, but we need to get rid of from the body. For example, toxins that can be secreted or metabolic wastes that are too large to be filtered into the lumen of the tubule, which would ultimately leave the body as urine with excretion. So the proximal convoluted tubule, again, does the majority of reabsorption, and the peritubular capillaries and the tubule lumen itself is at equilibrium. We do get an electrochemical gradient formed in the lumen of the proximal convoluted tubule cells. And so those cells are going to be able to take substances such as nutrient molecules like glucose and amino acids, vitamins, and so forth, and bring them across the cell with secondary active transport. Okay, so we're going to set up that gradient and then move the substances across that we want to move across with another molecule. And that other molecule that is used for that secondary active transport is sodium. Water can freely diffuse across the membrane cells, and so can urea. Urea is actually a small enough waste molecule that it can also pass through the phospholipid bilayer. In the proximal convoluted tubule, once we get those substances into the cell across the apical membrane, we then have to get it across the basilar membrane and into the peritubular capillary on the other side. That sodium that was used for secondary active transport will be actively pumped, so that's an ATP process. We've got a sodium-potassium ATPase, just like we've seen in other processes. So 3 sodium out for 2 potassium in. And then that potassium is going to leave by facilitated diffusion back out the basilar membrane into the extracellular fluid. Water, amino acids, vitamins, glucose, etc. all leave the basolateral membrane by facilitative diffusion. So we're going to have a channel, a hole in the membrane for those things to get through, but energy is not required. Urea, again, lipid soluble, it's very, very small and can freely diffuse out the other side of the proximal convoluted tubule cell. Waste, however, and yes, urea is a waste, but it's small enough to get through, so it's kind of a constant battle with urea. Some of it, just by chance, doesn't diffuse through the apical surface into the proximal convoluted tubule cells and will leave the body in urine, but some of it will get reabsorbed into the peritubular capillaries just because that molecule is small enough to cross those cells. Remaining waste, such as creatinine, and uric acid and other nitrogenous substances such as ammonia will end up staying in the lumen of the proximal convoluted tubule and become urine and leave the body in excretion. This figure isn't in your text, so it will be posted with your ink, but it's a nice diagram that shows you the mechanics of the substances going from the lumen of the proximal convoluted tubule and across those cells into the peritubular capillaries, and it will show you a little description of what's happening along the way. Glucose, amino acids, vitamins, ions, and so forth are going to do a secondary active transport, your little key is down there, into the cell along with sodium as a co-transporter. That sodium is going to be dealt with your sodium-potassium ATPase, so that requires energy. And the potassium that's coming in with that ATPase will just facilitatively diffuse along its concentration gradient back out to the interstitial fluid. Water can come in through simple diffusion, but a lot of it will come in through facilitated diffusion. Lipid-soluble substances such as urea and water will come in and right back out the other side through simple diffusion. All right, now with diabetes mellitus, there's only so many transporters in the kidney tissue, and you require sodium to be able to co-transport those substances in. So again, on this side of the membrane, normally the kidney can handle what glucose is coming through there and transport it through secondary active transport with a sodium ion. However, in diabetes mellitus, glucose is not being taken up by the cell. So when it comes into the peritubular capillary, it is in a much higher concentration than in normal physiology. And there's only so many of these transporters, so a lot of that glucose is going to end up leaving the body in urine. And so in diabetic individuals that are not treated, glucose is detected in the urine. Under normal conditions, the kidney can handle that amount of glucose. The amount of glucose that the kidney can handle and not have any end up in the urine is called its transport maximum. The transport maximum for the kidney for glucose is 375 milligrams of glucose a minute. So it can transport 375 milligrams of glucose across those peritubular capillary, across the proximal convoluted tubular cells into the peritubular capillaries. But if the concentration of glucose is any higher than that, it ends up in the urine because there just aren't enough transporters to get it through as the filtrate is passing through that lumen. Now, reabsorption in the loop of Henle. The loop of Henle is actually the major portion that determines how much water and sodium will be reclaimed back into the bloodstream. And the way the loop of Henle works is basically going to determine how much urine is voided per day, and that's going to end up being between 1 and 1.8 liters of urine a day. There are two different actions that happen in the loop of Henle. In the descending loop of Henle, the action is to reabsorb water. But in the ascending loop, going back up the loop of Henle, the action is to reabsorb sodium ions. Okay, and both of those are going to end up going into the peritubular capillaries. So what we get is the loop of Henle like so. And of course, this would be your proximal convoluted tubule. Let's write that where you can see it. Proximal convoluted tubule leading into the loop of Henle, and then coming out of the loop of Henle, you enter the distal convoluted tubule. Now, the filtrate concentration leading into the loop of Henle is going to be 300 milliosmolar. Okay, and so you know that that's a form of molarity based on the number of molecules exerting a pressure on the wall of the loop of Henle. But for now, it's a unit, 300 milliosmolar, that's representing a concentration. As the filtrate travels down the descending limb, so descending for down, loop of Henle, you're going to get water reabsorption. So of course we have our peritubular capillaries wrapped around the loop of Henle to capture anything that's reabsorbed. Okay, and on the way down, there are only channels that are going to allow water to leave the filtrate and be reabsorbed. So what happens to a substance when we take water out of it? If we have a solution and remove water, what happens to the concentration? Go ahead and try it, even though this is a video lecture. Right, it becomes concentrated. By the time we get to the bottom of the loop of Henle, the concentration measures about 1400 milliosmolar. Now, that's a number that you're going to see vary a little bit from textbook to textbook. The old textbook that we used said 1200, this one says 1400, but clearly much higher concentrated than when the filtrate entered the loop of Henle. Now, on the way back out of the loop of Henle, up the ascending limb, water is impermeable. Now, Clearly, some of it can get through by simple diffusion, but that's a very small amount compared to transport. So on the way back up, we primarily reabsorb sodium. So sodium is going to leave the filtrate and go into the peritubular capillaries. So what happens if we have a solution and we don't do anything to the water, but we remove solute? That's right, it's going to dilute or become less concentrated. By the time we leave the loop of Henle, the filtrate leaving the loop of Henle measures 100 milliosmolar. So we have a net dilution from the entrance to the exit of the loop of Henle, and a lot of that water and sodium has now been reabsorbed back into the cardiovascular system for homeostasis. All right, so sodium concentration increases as we head down the loop, and then it decreases on the way back up due to sodium reabsorption. Figure 14.8 shows you that process. Leading into the loop of Henle, we have 300 milliosmolar concentration. We're going to reabsorb water on the way down, reaching a concentration of about 1400. As we come back up, we are going to doing active transport to bring sodium out of that filtrate and back into the peritubular capillaries. And as we reach the top of the loop and begin to enter the distal convoluted tubule, we measure 100 milliosmolar. So a net dilution from start to finish. There will also be a net loss of volume. So we're not just unconcentrating it. We reabsorbed a lot of water going down the loop of Henle. So not only is it more dilute, but it is also a less volume entering that distal convoluted tubule. As we mentioned before, in the distal convoluted tubule, we can do some reabsorption as well as in the collecting duct. In the distal convoluted tubule, primarily ions are reabsorbed. We do have sodium, potassium, ATPase pumps, and so in non-homeostatic conditions, we can reabsorb some sodium. Potassium is pumped out, sodium is pumped in. Sodium is pumped out, and potassium is pumped in. And wherever that sodium is going to go, water is going to follow it by osmosis. And you saw an example of this when we talked about increasing water volume for control of blood pressure. And the hormone that triggered this was aldosterone. So aldosterone can actually cause, I don't know why that's happening. Aldosterone can actually cause an increase in the amount of sodium, potassium, ATPase pumps that we have in the distal convoluted tubule cells, and therefore increase the amount of water that is being reabsorbed, therefore increasing water volume. Now in the collecting duct, ions can also be controlled, but we also have aquaporins. Aquaporin is a protein pore or channel for water. And these typically aren't used very much unless you're in a non-homeostatic condition. So if you're severely dehydrated, for example, aquaporins can be triggered to be produced, which is going to, that would happen by antidiuretic hormone. The more aquaporins you have, the more water leaves the filtrate and becomes reabsorbed by the cardiovascular system, increasing your hydration. Collecting duct is also going to reabsorb bicarbonate ion, and we're going to see this next week in lecture when we talk about acid-base balance. And also urea. Again, urea is a small molecule and it does get reabsorbed. So it's a constant battle to try to excrete it because it is a lipid-soluble molecule. Table 14.5 summarizes all of the processes that we just discussed from the glomerulus through the tubular system and ending in the collecting duct. So it's a nice summary chart for you. Other role of the kidney was playing a role in blood pressure. So this is a little bit of a review from what we did with blood. But the juxtaglomerular cells, which were at the entrance to the glomerulus surrounding the afferent arteriole, let me just get to this diagram. These little aqua-colored cells right here, they had baroreceptors on them. And if those baroreceptors aren't stimulated enough because of a drop in blood pressure, that's going to cause the release of renin from those cells. And then, as we saw earlier, renin is going to convert angiotensinogen into angiotensin 1. Angiotensin 1 is converted into angiotensin 2. And one of the activities that angiotensin 2 could do was stimulate the release of aldosterone from the cortex of the adrenal gland. That aldosterone increases the sodium-potassium ATPases, which increases the reabsorption of sodium and therefore the reabsorption of water by osmosis, increasing blood volume. And this can happen not only at the distal convoluted tubule, but also a little bit in the collecting duct. And again, this would only happen if we have a drop in blood pressure. Figure 14.24 shows you that process. So if we have a drop in blood pressure, okay, we are going to trigger the release of renin from the juxtaglomerular cells. That renin enters the plasma and ultimately converts angiotensinogen into angiotensin 1, then angiotensin 2. And that is going to trigger the release of aldosterone from the adrenal cortex. And aldosterone increases in the blood plasma and is going to have an action at the collecting ducts, also at the distal convoluted tubule, by increasing sodium reabsorption by sodium-potassium ATPase, and therefore water follows it, and that will decrease the amount of water excretion and increases blood water volume through reabsorption. Antidiuretic hormone comes from the hypothalamus and also has an action on the kidney, as we saw in the past in the endocrine system. This hormone actually stimulates the production of aquaporin insertion in the plasma membrane of the collecting duct cells. And the aquaporin is to increase water reabsorption. And so the result is an increase of water volume in the bloodstream. Okay. So same effect that we saw with aldosterone, but different hormone acting on a different way in the kidney. And this happens primarily in the collecting duct. So another way that the kidney plays a major role in controlling water volume of the blood. Oh, there we go. All right. Figure 14.27 summarizes that process. So we have a decrease in blood pressure. That's going to cause the release of antidiuretic hormone. And of course, the other name of antidiuretic hormone is vasopressin, which they're using here in this example. And vasopressin then increases in concentration in the bloodstream, acts on the collecting ducts in the kidney to increase tubular permeability by way of aquaporins in the collecting duct cells, which leads to more water reabsorption and therefore less excretion or more water reabsorption into the bloodstream, leading to a greater blood volume. Now, tubular excretion is to remove substances from the blood to the tubules for excretion that were too large or too great of concentration to be filtered. So examples include excessive ions. So for example, excessive potassium can actually be actively secreted from the bloodstream into the tubular system of the nephron to be excreted. Also, proteins, for example, that are too large to fit through the filtration membrane, such as toxins in the blood, like bacterial toxins. These are all things that couldn't be filtered or filtered effectively, and we still have a last chance to secrete them. Tubular secretion primarily occurs in the proximal convoluted tubule. However, some can occur, primarily occurs in the distal convoluted tubule. However, some can occur in the proximal and the collecting duct. Okay, so we reach the collecting duct, and what is actually going to leave the body is a result of, so what we're going to excrete is a result of how much was filtered. So let's say we have 100% of what was filtered, minus what is reabsorbed, which is about 99% of the substances, plus whichever is secreted. However, that's negligible as far as this equation is concerned. It's a very, very tiny amount, less than 1%. So if you have 100% being filtered, okay, 100% of filtrate, minus 99%, how much do you have left? 1% will leave the body as urine. Now, 100% was 180 liters of filtrate a day. Okay, we're going to reabsorb 99% of that, leaving us with 1% of 180, which of course is 1.8 liters of urine a day leaving the body. So 1% is excreted, approximately 1.8 liters per day. And of course, that's going to have a range based on body size, how much you intake for fluids a day, and so forth. All right, some things that affect the kidney. Diuretics. Diuretics are any chemical that inhibits the work of antidiuretic hormone or sodium reabsorption in the body, therefore causing water not to effectively be reabsorbed and increases urine output. Things that can do that are caffeine, alcohol, hypertension drugs, which of course would be given on purpose to try to relieve edema conditions and so forth. We want to get rid of water from the tissue, and to do that we have to get rid of water in the bloodstream. And so that will also include some edema-specific drugs such as Lasix. Anuria. Anuria in Latin literally translates to without urine, but what it really describes is a decreased urine output than normal. This can be caused by a couple of things. Anything that decreases your net filtration pressure in the glomerulus, thus affecting the speed at which we filter, so your glomerular filtration rate. So things that can do that, any kind of trauma to the kidney, transfusion reactions where you have a lot of agglutination of the blood cells going on, clogging up the capillaries in the kidney, nephritis, inflammatory condition of the kidney, and high blood pressure situations, which we saw earlier, anything that increases that hydrostatic pressure. And finally, renal failure. Renal failure can result from the actual destruction or popping of the glomeruli. For example, if we have high blood pressure and are not able to homeostatically control it, we'll actually rupture those simple squamous endothelial cells of the capillaries, and then you get an inflammatory condition of the kidney. Trauma to the kidney. Some toxins, bacterial toxins, and medications can actually cause destruction of the glomeruli, and diabetes mellitus can as well. When you do get this condition, it causes an increase of permeability from the tubules back into the extracellular fluid, and therefore we can't regulate what is actually getting excreted. And of course, some things, as you know, like potassium, if it's not excreted in an appropriate quantity, it ends up building up in the bloodstream and can cause serious problems such as heart failure. That's the end of the lecture.